Hello guys, my name is Paresh and welcome to my YouTube channel. In the previous video we have discussed about the CNN, that is the Convolutional Neural Network. In this video we are going to build a project on the butterfly species classification. So let's start the video. For this project I have choose this dataset, that is butterfly image classification. This is available on the Kaggle. This dataset contains images of 75 different classes of the butterflies. It have total 9,247 images. Like any other dataset, this dataset also have some issues. Let's discuss this issue. The first issue is less number of images per classes. As you can see on the screen, this is the distribution of images per class. There are less number of images in all classes. Due to this, model can struggle to recognize the images. To tackle the issue, there are some solutions. The first solution is data augmentation. The data augmentation is a technique to increase the training data set. When you have less training data, in data augmentation, we apply the different transformation to the images, such as flipping the images vertically, horizontally, or the stretching and the changing the brightness of the images or the contrast. The second solution for this problem is using simpler model. Using simpler model or not using the complex model. When we have less training data, it is especially important to use a simpler model with the limited data. Complex model can easily memorize the data, the training data, instead of learning from that data. This is called overfitting. To avoid the overfitting of the model, we will use a less complex model. Less complex model is the model with few layers and the neurons. So the third solution for our problem is regularization. So the regularization is a technique which prevents the model from the overfitting. The fourth solution to our problem is early stopping. So the early stopping is a technique where you stop training the model once it stops getting better, to prevent it from learning noise and the overfitting. With this, we are also using the dropout. Dropout batch normalization. Batch normalization and learning rate scheduler. The problem number two we have is we don't have labeled test data. In the original dataset, they haven't provided the test label to us. So we will be evaluating our model on the validation data, and we'll use the test data to demonstrate the predictions. Now let's move to the pre-processing stage. I have organized the dataset in the folder species wise. The original dataset was like this. They have already splitted the data into the test and the train. Also, they have given one file called train.csv, which have image number and class of the image, such as image 1 is belong to the this class, image 2 is belong to the Adonis class, image 3 is belong to the this class, and image 4 is belong to monarch class. To make our workflow better and the smoother, I wrote a piece of code that take this CSV file and organize the train images according to the species. After running the script, I got the output like this. The data got classified according to the species like this. The original data was not labeled. It has name as image 1, image 2 like this. So I labeled the data using a Python code. This is the second pre-processing I have done. As I have discussed earlier, we don't have the labeled test data. To evaluate the model more performance, we need a validation data. So I split 10% of the test data into validation. I have used the stratified sampling to ensure that each class is proportionally represented in the training and the validation sets. And the last pre-processing I have done is the data augmentation. As we have the less training data, to increase the training data, I have performed the data augmentation on the training data and save that images. These are the augmented images. As you can see, these all are the augmented images. For all these steps, I have wrote a Python code. I will share all of this code with you. Now let's move to the main part, that is model building. I am building the model on the Kaggle notebook because Kaggle provides 30-hour free GPU, and as they have the image data, so on the local machine it will take time. So it is better option to choose the Kaggle notebook. To create the Kaggle notebook, you have to click on the create icon and click on the new notebook. And you have to upload data from the upload data tab, and you have to zip the dataset and upload here. And in the notebook option, you have to select the GPU T4X2 option to enable the GPU. Now let's build the model. First, we are importing the TensorFlow that will help us to build and train our model. Next, we are importing the image generator API from the Keras, which help us to load and process our data easily. Then the sequential layer, which help us to build our model layer by layer in a sequence. For the model layers, we are importing convolutional 2D max pooling, flatten, dense, dropout, batch normalization. We are choosing Adam as our optimizer, and we are also importing callbacks and regularization technique to prevent overfit our model. Now let's start with setting our path. In the train underscore dir, we have given the path where we have stored our training images. And in the valid underscore dir, we have given the path of the images where we have stored the validation images. Moving on, we are using the image data generator to help prepare our images. With the data generator, we are mainly rescaling the images so that the pixel value will lie between 0 and 1, making it easier to our model to process. Next, with the flow from directory method, we are loading our train images. We are setting the size of each images to 24 cross 224 in the batches of the 32, and categorizing them based on the classes we have. Similarly, for our validation set, here we have defined the couple of parameters, that is input underscore shape, which tells our model the size and the depth of the images it should expect, and the number of classes indicates how many different types of butterflies we are trying to classify. Transitioning to model improvements, we introduce the callbacks. Here early stopping, which stops our training if it notices no progresses in the validation accuracy for the 10 epochs. It also ensures that the best weights during parameters are stored in our model for the optimization performance. Next up, we have the learning rate scheduler. This adjusts the learning rate during the training. If the model validation loss doesn't improve for the two epochs, it scales down the learning rate by the factor of zero point 0.2. This ensures our model doesn't stuck and adapt as it learns. Alright, let's dive into the heart of our solution, that is the model architecture. We are using sequential model, which means we are stacking layers one after another, starting with the convolutional 2D layers with the 32 filters. We are using 3 cross 3 filters and apply the ReLU function. We also have added the padding, so our output maintains the same direction as our input for this layer, and subsequent ones we are using the L2 regularization, which penalize the weights and preventing them from becoming too large and overfitting. The batch normalization, layer normalization output from the previous layer, ensuring stable learning process. Then we downsize our images with the max pooling 2D. They help reduce computation and capture the essential feature. Dropout layers are sprinkled through the architecture. They have randomly turn off certain neurons during the training and promoting the better generalization. We repeat this pattern with increasing number of filters, 64, 128. After our convolutional back blocks, we flatten the data to prepare it for the fully connected layer. Dense layer with the 512 neurons act as a massive feature combiner. With the ReLU activation, it capture the patterns. And finally, the dense layer has as many neurons as our classes and uses the softmax activation to the output probabilities for the each butterfly species. Our model is set up. Let's configure the training process. We are using the Adam optimizer. It's known for adapting the learning rate during training, which makes it a popular choice. We are setting our learning rate at 0.01 for our model to learn from the correct pattern. It helps to understand the difference between its prediction and the actual labels. This difference is the loss, which we compute using the categorical cross entropy method. Minimizing the loss is the model's primary goal during the training. We are also tracking the accuracy, which tells us the percentage of our prediction model got right. Now that our model is set up, let's jump into the actual training process. We are training our model using the fit method. This is where our model will learn from the training data. Train underscore gen feeds batches of the training images and their labels into the models. We have set the number of epoch to the 10, which means our model will see the entire training dataset 10 times. We also provide the valid underscore gen as our validation data. It helps us how our model performs on the data it hasn't seen during the training. Finally, we are using the callbacks. We discussed earlier, early stopping prevents our model from the overfitting and stop training when it stop improving. And the learning rate scheduler adjusts the learning rate. Now let's train our model. After training the model, I got this result. In this training, I have run 10 epochs. Our model is learning step by step. It started with the accuracy of 70.5%, but with the each epoch, it learned a bit more, adjusting itself to do better next time. By the fourth epoch, it changed the learning rate to improve faster. After 10 epochs, we got the accuracy of 85.61 as the training accuracy, and the validation accuracy we got is 71.8%. I have plot this graph training versus validation accuracy. As you can see, the training accuracy is increasing, but the validation accuracy got some spike in between. I also plot the training versus validation loss. As you can see, the loss is decreasing per epoch. It is the good sign that our model is training. Here I have printed the classification report. Let's discuss this report in the detail. Reflecting on the result of our butterfly classification product, there is a clear indication that our model requires further refinement to be more effective. With the We got the validation accuracy of 75%, but the model is not successfully identifying the difference among the various butterfly species. This classification report demonstrate that many classes precision recall and F1 score at 0. As you can see, this suggests that the model fails to recognize the distinctive feature for the butterfly species. A notable observation from our data is that the several classes have the small number of samples. This class imbalance is likely significant factor for the contributing to the model suboptimal performance. Now let's discuss the future enhancement in our model. First one is the data runtime data augmentation. Implementing the runtime data augmentation can be beneficial, especially the classes with the fewer samples. By transform variations of the existing images such as rotations, flips, and zoom, we can simulate a larger dataset, potentially aiding the model's generalization capacity. Second is transfer learning. Retrain model like VGG16, ResNet, or Inception, which have been trained on the extensive dataset, might be leveraged for the better performance. Their learned features can be excellent starting point for our classification task. Third enhancement could be the model tuning. There is a need to delve deeper into the current model architecture. Perhaps the more convolutional layers or adjustment of the hyperparameter could optimize its performance. The exploration of the different activation functions, optimizer, or other regularization technique might be worthwhile. In wrapping up, while the current state of our model is far from the ideal, it serves as the learning point. The challenges encountered with butterfly species classification have provided the insight that will guide future iterations. With the suggested enhancement, there is a promising path forward towards a improved model. Thank you.